Okay, let's dive right into this. Welcome to the Explainer, where we're going to unpack one of the absolute most fascinating, kind of hidden mechanics of the modern internet: web security and digital trust. Every single day, we send incredibly sensitive information across the globe: passwords, credit card numbers, private messages, and it all relies on this invisible system of trust operating completely behind the scenes. So today, we're popping the hood. We're going to demystify TLS certificates, taking what usually sounds like a highly complex computer science lecture and turning it into a clear, logical story about how the internet actually defends itself.
Here is our agenda for today. We'll hit 1. The internet's trust problem. 2. Trust on first use. 3. Certificate authorities explained. 4. Proving who you are. 5. Certificate transparency logs. And 6. When trust is broken. All right, let's get to it.
Section 1. The Internet's Trust Problem.
So, the foundational question of online identity boils down to this. When you connect to a server, how do you actually know who you're talking to? I mean, sure, you establish a secure encrypted channel, but encryption alone is pretty useless if you don't know who is on the other end. Think about it. You type a URL into your browser, and a server somewhere replies, "Hey, here's my public key, let's start a secure session." But how do you know for sure you're really talking to Google? What if there's a man in the middle? An attacker just sitting on your network, intercepting your connection, handing you their own public key, and quietly reading everything. You'd be perfectly encrypting your data, but you'd literally be encrypting it directly for the attacker. Your browser desperately needs a way to verify that the public key it just got actually belongs to the domain it asked for.
Moving right along to Section 2, Trust on first use.
So before we look at the massive global solutions, let's look at the simplest layer of trust. If you've ever used SSH to log into a remote server, you've actually used TFU, Trust on First Use. Here's how it works. On connection 1, your computer essentially says, "Look, I have absolutely no idea who this is, but I'll blindly accept this public key and save it in a local table." Then, on connection 2, and every single connection after that, your computer checks that table. If the key matches what you saved, boom, you're good to go. It's super simple, requires 0 outside trusted parties, and protects you from future attackers. But, and this is a massive but, if an attacker intercepts your very first connection on day 1, well, you've just permanently saved the wrong key. You'll be handing your data to the attacker forever, or at least until you manually realize something is wrong. So TFU is neat, but it's definitely not robust enough to secure the entire World Wide Web.
Which brings us to Section 3, Certificate Authorities Explained.
Enter the Certificate Authority, or CA. These organizations basically act as the internet's passport offices. The whole concept hinges on the CA being a trusted third party. Instead of your browser just guessing if a public key is legit, the server hands over a digital ID card, a certificate. The CA holds this gigantic logical table mapping domain names to their correct public keys. When a server needs to prove its identity, it shows your browser a statement from the CA that effectively says, "Hey, we mathematically guarantee this specific public key belongs to this specific domain." The CA then cryptographically signs that statement with its own secret key. Your browser checks the math on the signature, and just like that, identity verified.
But wait, I know what you're thinking. It's the classic chicken and egg problem, right? How does your browser know it can actually trust the CA's signature? Who put the CA in charge? Well, the answer is actually delightfully simple. It's baked right into your device at the factory. When you buy a laptop or download Chrome or Safari, the source code literally contains a hard-coded list of roughly 100 highly trusted root CAs. We're talking major tech companies, international orgs, and popular free CAs like Let's Encrypt's ISRG root. Your device trusts them simply because Apple, Microsoft, or Google made a policy decision to trust them before you ever even press the power button.
All right, Section 4, Proving Who You Are.
Let's dive into the actual mechanics here. How does a CA genuinely verify a server's identity before handing out that super trusted digital ID? They use automated verification protocols. The most famous one is called ACME. Let's walk through this, it's pretty cool. Step 1. The server goes to the CA and says, "I control this domain, please sign my public key." The CA replies, "All right, prove it." It generates a totally random string of data, a nonce challenge, and tells the server to host that exact string on its public website. So the server sticks the random value on its HTTP port. Then the CA's validator reaches out across the internet, requests that specific URL, and checks for the nonce. If the validator sees the correct random string, it logically proves that whoever asked for the certificate genuinely controls that domain name.
But, of course, attackers are clever. A really sophisticated attacker might try to hijack the network route between the CA and the server just to fake the response to that challenge. To shut that down, modern CAs use multi-perspective validation. Organizations like Let's Encrypt don't just check the challenge from one single server. No way. They check it from 3, 4, or even 5 different validation servers scattered all over the globe. Sure, an attacker might be able to spoof a connection from one localized spot, but simultaneously intercepting traffic from 5 different global perspectives, that's almost literally impossible unless they control the victim's underlying network infrastructure. It's just a brilliant cat and mouse game.
Now for Section 5, Certificate Transparency Logs. So what happens when a CA just messes up or gets tricked? We need public accountability, and that failsafe is the Certificate Transparency, or CT log. Think of it as a massive, public, append-only ledger. Browsers literally force CAs to publish every single certificate they ever issue to these logs. In fact, before Chrome or Safari will even accept the certificate, it has to contain a cryptographic receipt proving it was published to a CT log. This means there's no such thing as a secret certificate anymore. If an attacker somehow tricks a CA into issuing a fake certificate for your website, it absolutely has to be published here for the entire world to see. Domain owners constantly scan these public tables, hunting for rogue certificates so they can sound the alarm immediately.
And sounding that alarm brings us to our final part, Section 6, when trust is broken.
We have to talk about the messy reality of what happens when a private key gets stolen and you need to kill a certificate before its natural expiration date. The history of revocation is just a wild ride of computer science compromises. At first, browsers would download these massive certificate revocation lists, CRLs, maybe once a month, but they were bloated and basically instantly out of date. So the industry pivoted to OCSP, where your browser checked the CA in real time on every single connection. But that added brutal latency and honestly destroyed user privacy because suddenly the CA knew exactly which websites you were visiting. To fix that, they invented OCSP stapling, where the server fetches its own revocation status every hour and staples it to the connection. Better, but still clunky.
Which leads us to the ultimate, honestly kind of hilarious conclusion of this entire saga. Basically, no revocation plan works well, so they're just going to shrink the expiration dates to be very short. After years of engineering incredibly complex protocols, the security community realized the easiest fix was just letting them expire faster. If a certificate is only valid for 90 days, or as is being pushed for now, just 7 days, you almost don't even need a revocation plan. If your key is stolen, you literally just wait a few days, the certificate naturally expires, and the attacker is locked out. And because of the automation we talked about earlier, like ACME, refreshing a certificate every week is totally painless and invisible for servers.
But I want to leave you with this final, really provocative thought. As the modern web races toward all this automation and these digital ID cards shrink down to incredibly secure 7-day lifespans, what happens to the older legacy internet? What happens to that smart appliance or that old router sitting in your closet? You know, the one that relies on a hard-coded 20-year-old CA list and just can't update fast enough to handle rapid certificate cycling? The internet's web of trust is constantly evolving to become more secure, for sure, but that very evolution risks leaving older hardware permanently out in the cold. It's a fascinating trade-off in the relentless pursuit of digital security. I really hope this explainer helped you grasp the incredible layers of trust happening behind your screen every single day. Thanks so much for joining me, and keep learning.